Welcome back to Rudy's Electronics Labs. And last week I posted a video which was about the FFT functionality of 3 different oscilloscopes. And in that video I also talked of things like resolution bandwidth, FFT resolution and frequency interval. And after that there was an interesting discussion on the EEV blog. Are these things the same or are they not? How do they relate to the main FFT system parameters that are chosen? And on the basis of that discussion I wanted to post a follow-up video where we actually focus on those aspects. Several people contributed by providing comments and thoughts here, and I'm particularly thankful to 2N3055 and to Performa01, both on the EEV forum, that have proved me willing to go into further discussions with me about the topics I'm going to talk about in today's video. So let's get started. The manuals of all of the 3 devices talk about something, either the resolution or the bandwidth when using FFT analysis. So the Rohde Schwarz RTB has a parameter called the resolution bandwidth, RBW, which is a value that is shown on the screen but also can be selected by the user, and it's explained as determining the resolution of the spectrum. And they also explain that it determines the minimum distance between distinguishable peaks, and the higher the resolution, the more peaks are detected. Okay, the Siglent talks of a so-called frequency interval, delta F, which is explained as the distance between 2 adjacent points in the FFT sequence. They also explain it is proportional to the frequency resolution, so it's not the same. Apparently there's a factor in between them, and actually we'll explore that later on. And finally the Keysight talks about the FFT resolution, and they don't explain what it is, but they explain how it is calculated, the quotient of the sampling rate and the number of FFT points. So we got a bit of information here, but it certainly doesn't tell us all about what this really is and whether these are the same thing or different things. And I'll start my exploration to talk about the resolution bandwidth, which is terminology that we already know for many years and is used on classic spectrum analyzer. And what is this really about? So if we have a measuring device like a spectrum analyzer, we might have an input, and in this example on the left is the example is given of 4 different tones of different frequencies and strength. And then we have the result which is shown by the device. And depending on the resolution bandwidth, we might be able or not able to have enough resolution to see these individual tones. So for example, in the picture in the middle, you see a device which has a large resolution bandwidth, which basically means that with this resolution bandwidth we cannot distinguish the tones 1 and 2 separately, or 3 and 4 separately. We just see 2 peaks in our final result, and we don't know that this actually comes from 4 different tones. Well, the picture on the right shows an output with a small resolution bandwidth, which is better basically. And here we see basically that the device is really able to show all the different peaks separately by itself, by having the bandwidth small enough. And to illustrate this, I actually took my spectrum analyzer and I created these 4 tones. So I took 2 signal generators, each of them can generate 2 tones, and I used the combiner. And I set my spectrum analyzer to a large resolution bandwidth, and I got a picture on the middle bottom, and I set it to a small resolution bandwidth and I got the picture on the right bottom. So we actually see here that in the large resolution bandwidth the device is not able to show this actually comes from 4 different tones, while with the small resolution bandwidth it is perfectly able to do so. And where does this resolution bandwidth come from in a classic spectrum analyzer? Well, it goes beyond this video to explain the complete work of a spectrum analyzer, but I'm taking here the block diagram of a very classic analog spectrum analyzer, one even with a CTR tube. And basically in order to show us the spectrum, it sweeps across the spectrum with a filter. And what happens in reality is not so much that the filter sweeps across the frequencies of the range that we want to look at, but the input signal is fed via a mixer and actually shows the input signal that moves within a certain window, and the IF filter decides what's being picked up and shown on the screen. Now this IF filter can have various characteristics, and the important characteristic that we are interested in is actually the bandpath properties, and so what it is passing within 3 dB of its maximum transfer. And so this is precisely the resolution bandwidth. We got this IF filter set to a particular bandwidth, and that determines how precise or how coarse we can see different frequencies distinguished from each other. Now moving to the FFT domain, as we talked already about in the last video a little bit, with FFT we actually have a computer algorithm that transfers the time domain information in frequency domain information. And the thing is that is important for our video today here is that this frequency information, which is the output of the FFT algorithm, is not something continuous, but it's actually information that is in a certain number of bins, and each of the bins has a particular width and has a particular value associated with it. Now our next step is to understand the width of these bins in the FFT analysis, because that is a very important parameter here. Now the width of these bins is defined by the sample frequency divided by the number of time domain samples. Now the sample frequency, that is the sample frequency of course by the oscilloscope, for example, using, but it's important to know here that we really should look at the sample frequency that is used as an input for the FFT algorithm. That might not be the full sample frequency as the device is running on, because that actually might have too many observations to be processed by FFT, and then decimation might take place. They might make a selection of those. So we need to know the sample frequency going into the FFT to know something about the bin width. And then the n parameter is the number of time domain samples that is used in the FFT function, and that is often referred to as the FFT points, like 64K FFT points or 128 K FFT points or 2 mega FFT points. Also here it's important to know the number of points that is actually used for the FFT analysis, and not just the maximum that the device can handle. And now going from this bin width to the resolution bandwidth is actually quite simple, because the only thing we need to do is multiply the bin width with a factor of k, and k is a window related coefficient, and that has been determined for a variety of different windows used in FFT, and in the table at the right bottom of the screen right now shows you the typical values for k for various types of windows. Now let's go to our oscilloscopes and try to see if we would apply these formulas, if it actually makes any sense here. So I'm taking a input signal of 800 kilohertz and I'm feeding it to the oscilloscope, simply a sine wave signal. I'm going to look at the oscilloscope, what type of values they actually do show us, and I'm going to try to plug in them into the formulas here. And so on the right bottom you see exactly the two formulas I showed on my previous sheet. And I'm indicating in green those values that are actually shown on the device. I'm showing in purple color what is known from theory, like the factors. I'm showing in yellow what can be calculated but what is not shown on the device, and if relevant I'm showing in red what information is not available at all. Now let's look at our SDS oscilloscope here, and it got a very nice little info window here where we find the various values that we're interested in. We see the sample rate, and that is the actual sample rate being used for the FFT process, because the overall sample rate of the device is shown all the way at the bottom in the time box window, and sometimes the FFT window is different if fewer values are being fed into the FFT. So we got a 20 M here. We got the number of FFT points. In this case this is 2 262,000, so it's set to 256K, but the 256K, as we also see it in the menu on the screen, that is basically K as in computer language, 1024, and the current value as it's shown, it is in the regular SI value, so we have to multiply by 1024, so that results in the value of 262144. So our formula basically told us then the bandwidth should be 76.29 megahertz, and that's exactly also what the screen of the Siglent oscilloscope is telling us. So that is great. Now, if we then also would like to know what the resolution bandwidth is, then we simply have to multiply by the factor that I talked about before. So 3.73 times the bandwidth that we had. So that should mean that the resolution bandwidth should be 284.6 Hertz, according to our calculations. But do these calculations also correspond what's actually happening in a device and the abilities that is able to show distinguished tones? Now, I'm showing you the next picture now in which I'm having the same signal as before, but I'm just focusing only on in the peak. So I've changed the vertical scale to 2 dB per division, so I can easily count basically dB values. I also changed the width of the display a little bit, I think, and I'm now trying to find with my cursor the -3 dB points of that particular display here, and I've set the cursors at this value, at the -3 dB points, and I'm looking at the difference between the lower frequency and the higher frequency, and the cursor measurement shows me that is 270 Hertz. And that is very nice, because that is almost the same basically as our calculated resolution bandwidth of 284 Hertz. So the Siglent does exactly what we expect it to do. It doesn't show the resolution bandwidth by itself, you have to calculate it. Wouldn't even be nicer if it would have shown it to us using this table version itself, but we can't complain about this. I mean, the Siglent is very predictable, I think, when it comes to FFT calculations. Now I will look at the Keysight here, and it's got a bit of information on the screen as well, and that information is called the FFT resolution, and that is actually the bandwidth, which I'm plugging here into my calculation. But where it comes from in terms of sample frequency and the number of FFT points being used, this we don't know. The device doesn't show there. If we go all the way back to the upper menu in the hierarchy, we see a sample rate, but that is clearly the overall sample rate and not the decimated sample rate that goes into the FFT calculation. And the number of FFT points, which is a maximum of 64K for this oscilloscope, the actual number used in a particular situation or calculation is not shown either. So we kind of left in the dark exactly where this bandwidth is being based upon, but it is being displayed. Now, also from here, in the same way as before, we should be able to calculate the resolution bandwidth by multiplying the bandwidth with the relevant factor for the flat top window, and that should be then 355.8 Hertz according our calculations. And do our calculations make sense? Again, I'm going to look at the actual waveform being displayed, and again I'm going to zoom in only on the peak we're seeing here and trying to distinguish the -3 dB point. So again, I've reset, or I set again the vertical axis. So the vertical axis is now at 2 dB per division, so 1.5 division is going to be 3 dB. I'm going to identify the 3 dB points of my wave. I'm going to use my cursors to measure the difference in frequency between these two 3 dB points, and my cursor basically measures 341 Hertz. Well, the calculated value was 355, so I think that's perfectly fine. So the Keysight is also, I think, predictable in a sense what it's doing here. The only thing is that I really would have liked to be able to see the actual sampling frequency as it goes into the FFT domain and the number of points, because I don't know exactly where it comes from. I'm left a little bit in the dark, but still, if I look at the waveform, you know, it all makes sense. And now to the Rohde Schwarz RTB, and I took this as the last one because it seems to be a little bit more complicated. So if I look again at the same type of test and I identify on the screen what I can find, I see the sample rate of the device, or at least what I thought to be the sample rate, but I'll come back to that later. I'm seeing the resolution bandwidth, so this is something we can directly observe and even set on the screen. And we can actually also see the number of FFT points. For that we have to go out of the FFT menu and we have to go to the acquisition menu, so it's hidden a little bit somewhere else, but if we go there we actually see the points, 131 kilo samples. So again, that's being expressed as SI value, not as computer value. So this is actually 120k time 1024. So plugging these values into the formula for bin width, we divide these on each other, the sample rate and the number of FFT points, and we get 15.7 Hertz, which apparently must be the bin width in our calculation. And then if we want to go from bin width to resolution bandwidth, we have to multiply again by the factor for flat top. And when we do so, we would end up at 58.3 kilohertz. And indeed, that is the same resolution bandwidth as the device is showing itself on the screen, 60 hertz. So up to here, that all looks fine. Like with the other devices, I'm also going to try to confirm then looking at the actual waveform. So again, I'm trying to zoom in on the top. That was a bit more difficult on this device because I cannot make the span smaller than it is right now. So I get a very narrow peak, even if I change the vertical scale only. I'm trying to set the cursor again to identify the -3 dB points. However, the cursor settings are not continuous, they go in certain steps, and I was not able to get exactly to the -3 dB point. So I'm looking here at about -6 dB points. Now this is a very steep line, so the difference is not going to be enormous, but I expect the value to be slightly higher. So if I use these -6 dB or whatever points, I see a difference of 78 Hertz, and that is indeed a little bit more than the 60 Hertz that I was expecting to find here. So also that makes perfect sense up to this point. And why did I just say up to this point? Now the thing is that if I go to a larger resolution bandwidth, I actually did so because I thought I could set my cursor better at 3 dB. Points. Actually the values for the sampling and for the record length remain the same. So the bin width should remain the same, and then if I multiply by the flat top factor, then I get a resolution bandwidth of still 58 Hertz, while in reality the device is showing me some 350 Hertz for the resolution bandwidth. And if I investigate the shape of the signal, zooming in on it again, and now I'm able to take the -3 dB point, what I actually see is a value that is 359 Hertz, so it's very close to the 350 shown on the device, but very different to the calculations that I made on the basis of the sample frequency and the record length. So where does that leave us with the Rohde Schwarz oscilloscope here? So to recap, in this oscilloscope, the calculation, if we choose flat top window with a smaller selectable resolution bandwidth, they're spot on, is what we expect. But if we take other values for the resolution bandwidth, we get something which is different from theory. Now I suspect that the sample rate that we see on the screen of the scope is not the actual one being used for FFT, basically like in the Keysight. And then we can only speculate what is really going on there. Could Rohde Schwarz be using oversampling here, and if so, why they would do so? Normally, for a higher resolution bandwidth, you would simply increase the sampling frequency. But by doing so, you can possibly generate different spurs that come from aliasing, and maybe Rohde Schwarz didn't want the look of the spectrum to change when you alter the resolution bandwidth, and decided to oversample and kind of emulate the resolution bandwidth after that. And if this is true, then it's something like a second step, and that may remind some of us of the so-called video bandwidth settings that we know of classic spectrum analyzer, which is also a second step carrying out after the regular analysis. Now again, this is all speculation, and whatever they are doing, for me it's like a black box, and we don't get to know what the actual main FFT system parameters is. And this is a bit of an issue, because if we don't know the actual FFT sampling frequency, we also don't get to know the Nyquist bandwidth, which is half of that frequency, and we also don't know whether the settings we've selected are appropriate for the type of input signal that we want to analyze. Alright, now coming to the conclusion, and on this sheet you see what the various devices offer as information or don't show, and as well as the overall conclusions. And starting with the RTB, some people have criticized the RTB for having some simplified form of FFT interface in which you don't get to see the real information that you need. And even though personally I kind of find it nice to see the resolution bandwidth, because it allows you to operate the device more like a spectrum analyzer, I must agree with that criticism. The lack of information on the decimated sample rate and the bin limit really limit our understanding in terms of what's going on in the device, so it stays a little bit of a black box. The Siglent SDS is doing quite well in respect of information, is giving us all the essential information. We don't get to see the resolution bandwidth, but of course we can calculate that ourselves. Should it be shown there, you know, that would even be nicer, but I'm fine with this solution. And finally, the Keysight DSOX. Well, also here we miss a lot of essential information on the actual decimated sample rate, on the FFT points that are actually used in an analysis. We get the bin size, from there we can calculate the resolution bandwidth, but also here I'm critical and I don't really have the information to know what's going on inside the device. So in that sense, the Rohde Schwarz RTB and the Keysight DSOX get the same type of criticism for me here. And that brings me to the end of this short video. As you might have noticed, I had a number of references to sources on the earlier pages, and on this last sheet you see the sources that I've used to prepare this little video. Hope you find it useful, and I'll soon be back with some further product reviews. Thanks for joining the channel.